Everybody, and welcome to a new series here on my channel called Simulation Deep Dive, with a particular focus on STAR-CCM+. If you're new here, my name is Jousef and I'm an engineer based in the Netherlands, and on this channel we explore systems, ideas and tools that help you become a smarter engineer. Today we're diving into our very first simulation of the Deep Dive series, namely the iconic 6215 Airfoil. But before we jump into that, maybe let's take a moment to appreciate the historical significance of that airfoil. The 6215 profile is part of the 6 series airfoil, which first saw action during World War II. Yes, you heard that correctly. Our airfoil today is a true veteran. Development efforts were undertaken by NACA in the 1930s to develop airfoils capable of longer runs of laminar flow. There are a couple of standout features that make the 6215 profile a great choice for our simulation today. Firstly, it allows for a positive angle of attack due to its streamlined design, resulting in less turbulence and greater steadiness. Second, it boasts a thickness of 15% of the chord length and a design lift coefficient of 0.3, making it a versatile choice for a wide range of applications. One of the key achievements of the 6 series airfoils was the ability to delay the onset of compressibility effect at high speeds, making them an excellent choice for high-speed, high-altitude flight. And if you think the 6215 airfoil is a thing of the past, well, let me tell you that it's not just a historic relic, but also a subject of cutting-edge machine learning research. And I will put some papers of the research down in the description. Studies have actually been conducted to optimize airfoil shapes using machine learning algorithms, with the 6215 profile playing a starring role. So, with this rich history, versatile performance characteristics and continued relevance in modern aerodynamic studies, the 6215 airfoil is an excellent subject for our today's first episode of the STAR-CCM series. As we delve into the details of this simulation, we'll not only be studying a piece of aeronautical history, but we'll also be equipping ourselves with the knowledge and skills to shape the future of flight. The first steps now will be to use an airfoil plotter and generate a 3D model inside of STAR-CCM+. And as we move forward in our simulation journey, our next step now is to use a handy website called airfoiltools.com, and this is where we'll create a profile of our 63215 airfoil. Simply enter the part number in the search bar and voila, there's our profile. With the magic of this tool, we can then adjust everything from the chord to the pitch and a few other parameters, even down to the grid size of the plot. And for this tutorial, we're using a pitch degree of 5. After plotting, save the profile as a CSV for the coordinates. This file then contains our airfoil shape in a format that STAR-CCM+ can understand. However, before we can import this into STAR-CCM+, we need to make some adjustments. STAR-CCM+ reads the values in meters, which is very important, not millimeters. So we need to divide our values here by 1000. We also need to add a third column, which is the Z column, filled with zeros, and we are treating our 3D model basically as a 2D surface. So we need to apply a function of products here first, then we select the first value and divide it by 1000. Let's then extend this for all the values on the bottom and for this column for the second column. So this is actually going to be fed as meters to STAR-CCM+. So this is eventually going to be, for example here, 8.7 millimeters. But STAR-CCM+ is going to read these meter values, as I already said, and we need them in millimeters. So we need this is the X, and this is Y, and then this is Z. So select, we add 0 for Z, the very first, and then hit Control and double click on this so that we have it an extended row of zeros until the last value of the previous column. So once we have gotten this, copy these values to a new Excel sheet, just open a new spreadsheet or a new tab, whatever, and create a new tab, for example here now on the right. We paste these numbers, go to File, Save, and save it wherever you want on your machine. And we'll give it a specific name, select CSV, and the delimiter will be CSV file, so comma separated value, and then click Save. Once the file is saved, we close the file, and the next step is going to be basically creating a STAR-CCM simulation from scratch. So we go to Geometry, create a new geometry, and we'll have this part created right here. Next step is to go to Edit and right click here, Import 2D Curves. Once you are in 2D Curves, you select this file. That file will be opened up as a text. So I'm going to show this to you very quickly. So we will get only the sketch. This is just a 2D span that you can see here on the screen. And this is the sketch. The next step, we are going to basically create a rectangle around the airfoil. And there's a few best practices. So for example, how big does the box have to be so that the boundaries of the box does not influence the fluid flow behavior around that airfoil. But there's even a few publications, papers around it. I think even not a few, but I think a couple of hundreds or thousands of publications talking about this. You need to make sure that we're not using body interaction, no merging, no imprinting. And the reason specifically is that we're going to use the subtract body function that is built inside of STAR-CCM+, which is a very handy feature. In the next step, do the same thing for the rectangular that we have created, or the box, and then apply the subtract Boolean operation by selecting the two boxes or elements. Go to Boolean and reduce and subtract. It's basically as simple as that. The next step is to name the surface for the air inlet. Right click it, rename it, and name it air inlet. Similar on the back, right click, rename air outlet. And right now, as you can see, this face is hidden. And let me show you how I did that. So select our face, right click, and then we have the option to hide it. So hide it and name first these elements as airfoils. So all these named faces are going to be showing here on this left toolbar. Similarly, we need to define the symmetry planes on right and the left. So I have used symmetry 1 and symmetry 2. Afterwards, we click Update 3D CAD and close 3D CAD. The next step is right click here and a new geometry part. In here, we are going to have this single part that we have just created. So click here and Update. And then we basically have it. Our 3D model is set up, our airfoil is in place, we set up the naming conventions for our boundaries, and now I think we can delve deeper in the world of simulation. Having created our 3D airfoil model now, ladies and gentlemen, we now venture into an indispensable stage on our computational fluid dynamics journey, which is meshing. Even though we have a 3D model, we are only interested in a 2D analysis for this study to make it very simple for the first video of the series. Fortunately, STAR-CCM+ allows us to treat a 3D model as a 2D surface. To make this happen, we'll create a so-called batch for 2D meshing. Head over to Operations or to the Operations panel, select New Mesh, and then Batch for 2D Meshing. Here we select our so-called airbox part and execute the operation. Next, we go back to the Operations panel, select Mesh, and then Automatic Mesh for 2D. In 2D, we have several mesh options, as you can see: polygonal, quadrilateral, or triangular. Triangles and quadrilaterals are perfect for simpler studies, but for a more detailed capture of the simulation, we'll use a so-called polygonal mesh. After choosing our mesh type, we execute the operation to generate our mesh. In the Scenes panel, you will now notice two scenes: Geometry and Mesh. These can be defined by navigating to Scenes, then New Scenes, and selecting Geometry and Mesh. Diving into the specifics of our mesh, the base size is set to 1 mm and the target surface size is 5 mm for the entire region. We'll also define 5 prism layers to create a refined region, or refined surface actually, around the airfoil, simulating the boundary layer of air directly adjacent to the airfoil. And if you want to know how to actually calculate, for example, how many layers you need, how big the size have to be, I'm going to link 1 or 2 videos down in the description that you can check out, where Aidan Wimshurst from Fluid Mechanics 101 explains in a very nice manner on how these cells, or how the distances actually are being calculated. So make sure to check them out down below in the description. And a prism layer, what are these prism layers? The prism layer add actually a prismatic cell layers next to the wall boundaries. And this layer of cells are created next to the wall boundaries to actually improve our accuracy of the flow solution as prediction of various flow features. For example, let's say we want to evaluate drag or pressure drop. So this has to be very, very accurate. So let's move on. This defines our mesh conditions right now, and we can further make it more refined by reducing this base size and further controlling this target surface size that you can see right here. And we can further play with this prism layer. But this is already a very optimal number, I would say, of prism layers to give us the boundary mesh layer results that we're going to observe in the coming plots and visualizations sections. Specific to this airfoil, we've defined a new surface control with a target surface size of 1 mm. While these parameters can, as I said, be further improved and adjusted for more refined meshing and more accurate solutions, what we have here provides an optimal balance between precision and computational cost, because we don't want to calculate this simulation for like 3-4 days. We want to have it fast and first insight, but still be kind of accurate, quote unquote. And with that, our mesh is ready to go and we are one step closer to launching our simulation. So now let's move over to step 4, region setup with boundaries. Having prepared our mesh, we now move forward to the crucial part of our simulation journey, setting up the region and defining the boundaries. To begin with, we'll create a new region. We navigate to region, as you can see right here in the region section, and assign the region to our part. With our region now defined, it's time to set the boundaries. We have the air inlet, obviously, we have the air outlet, we have the airfoil as the body, and the symmetry planes. To create a new boundary, simply right-click in the boundary section and select New. For each boundary, we'll select the corresponding path surface. For instance, for the air inlet boundary, we select the air inlet path surface. The default boundary type is automatically assigned to parts or regions where we haven't defined the boundaries. So for our purposes, we're not concerned about the top and bottom regions. However, the symmetry planes on the left and right are important, so we'll make sure to assign them to symmetry plane or a symmetry plane boundary condition. And just like that, our region is set up and our boundaries are defined. We are now basically ready to delve into the exciting part of the physics setup, where you can mess up a lot of things. So physics setup, part number 5 or step number 5 of this whole process. Now, just to repeat, now that we have set up our region and boundaries, let's turn our attention to the physics of the simulation, which is going to be very, very crucial, because there are a lot of options and parameters that you can tune and tweak to make this either more accurate, less accurate. So this also is based a bit on experience, and when in doubt, always look up some papers or publications to make sure you're dealing with a specific problem. Make sure to use an accurate turbulence model, for example, for your specific problem. But how do we do it for this simulation right here? The first setup is a steady model. This model assumes that fluid properties do not change over time, which makes it an ideal for simulation with stable, time-independent flow conditions that we want to deal with in this very simple first step. For our airfoil, what does this mean? This means we're assuming steady-state conditions with no changes in angle of attack or speed, for example. Next, we're defining our simulation as two-dimensional, as we've already talked about in the beginning, using gassed air as the medium and segregated flow conditions. The segregated flow model solves flow equations one at a time, which is less computationally expensive or intensive than a coupled solver where all the equations are solved simultaneously. However, for highly coupled flows where the pressure and velocity coupling is strong, a coupled solver might be more appropriate. But again, this is a separate topic. We could do like a whole video on coupled solvers, etc. But for this video, we're gonna assume what we're assuming right here, and we move forward with that. So start simple and then build up in terms of complexity, just to also debug a simulation way easier. So if you might have seen some of the CFD podcasts on this channel, you might notice that almost all CFD experts always say, take your problem, simplify it to like the most simple model that you could choose and kind of increase the complexity step by step. And then you will basically see if you increase the complexity by a little bit and tweak one more parameter, but the outcome is garbage, you kind of can debug it very easily in saying this specific tuning of my model actually caused the simulation output to be garbage. So I kind of can go one step back and kind of think again or rethink the parameter that I've tweaked. Okay. With that out of the way and a lot of rambling out of the way, let's now go to the density settings. To simplify our flow physics, we're choosing the constant density model, which assumes that the fluid density does not change significantly throughout the flow field. And this is quite appropriate for incompressible or low speed flows. As airflow around an airfoil can become turbulent, we've chosen the turbulence model. Specifically, we're choosing the K omega model, a two-equation model that is well suited for simulating near-wall turbulence, boundary layers, and free shear flows. Again, there are some few best practices that you could choose from. For example, what turbulence model to choose. Again, for an airfoil, there are pros and cons for different turbulence models, but for this now we're choosing K omega. We're also using the all Y plus wall treatment, which can handle a wide range of Y plus values, crucial for accurately capturing the boundary layer and wall shear stress. Some closing remarks now. It's important to remember that the selection of these models depend on the specific conditions of the airfoil simulation. And it's very important, ladies and gentlemen, to balance computational efficiency and simulation accuracy, which is key. Different models might be necessary for different conditions, different flow conditions, and maybe airfoil designs. Now, as we delve deeper into the physics setup, you may wonder, why have we even chosen the K omega model when many people use the K epsilon model, for example, for turbulence modeling? Let's maybe give you a quick intro and kind of break down the reasoning behind all of that. So firstly, K omega model excels in boundary layer resolution, and the K epsilon model, which is very important, can be less accurate in the near wall region because it kind of makes the assumption about turbulence or the behavior of turbulence in the near wall region. And it's very important to accurately model the boundary layer behavior, especially for airfoil simulations, as it's kind of significantly influencing like lift and drag and all these parameters that we'll have a look at and kind of the post-processing stage. For this reason, we've chosen K omega as kind of a best practice. But again, it really depends on your use case. If you go from airfoil to, let's say, backward facing step, the turbulence model might be a completely different one. But again, it depends on the physics that you're trying to resolve or actually trying to solve. So model stability and convergence. For complex flows in geometry, the K omega model can actually offer better stability and convergence behavior than the K epsilon model in general. I'm not talking about all the scenarios, but I'm talking very general. And stability and convergence, as you might know, or as you will learn, is very key to having like a successful simulations, making this another point, kind of giving it a favor basically for K omega, the turbulence model. And you will see if your simulation is not converging, you kind of get a lot of headaches. So kind of looking up best practices on what turbulence model to choose can save you a lot of brain cells and also a lot of sweat and tears. Finally, the K omega model is typically more suitable for flows expected to transition from laminar to turbulent, as it is the case usually for our airfoil. And some versions of the K omega model, like the SST model we're using, offers robust handling of transitional flows, which isn't really possible with the K epsilon model. Maybe as kind of a summary for this section is that it's really important to remember that the choice of turbulence model hinges on the specific requirements of the simulation, and kind of you have to have a balance between kind of the accuracy and the computational cost at the end of the day. So while the K epsilon model, as we've said, could be a good choice for other type of flows, for our airfoil, the K omega model kind of reigns supreme in this case. I hope this kind of clarifies our choice and helps you kind of make an informed decision in your own simulations. So really think about, especially setting up the physics and boundary conditions, that the choice of turbulence models is really crucial, and it kind of goes hand in hand with the meshing. So if you screw up the mesh, if you screw up the turbulence model, you kind of can start from scratch. So always think about how you want to approach a simulation, start easy, and then increase in terms of the complexity. Now, ladies and gentlemen, with all of the preliminary skirmishing, let's set up our simulation, which is going to be the exciting part. So buckle up. But first, let's define some initial conditions and reports first, because we have to define initial conditions, and especially for the report, it's going to be important what we try to evaluate. So as you might have learned maybe in a CFD course, maybe of one of my podcasts, it's very important to think about the quantities that you're trying to get from a simulation. So this defining report is going to be important because we want to define the quantities that we're going to have a look at in post-processing to kind of evaluate our flow around the airfoil, lift, drag, and a few others that might be important. But again, it depends on the use case, what quantities are going to be important. Initial conditions. So although the pressure is set to a default zero reference, we don't want our airfoil to be stagnant. So remember, our airfoil is part of the wing already in flight. So it's kind of encountering the airflow. So to reflect this, we'll define a head-on velocity in the x direction of 60 kilometers per hour, which is about 17 meters per second. And with our physics setup complete, we'll define some reports to track the downforce and the drag. So we only have a look at downforce and drag. And we'll go to reports, select new report, and choose flow energy and force. For the downforce, we're interested in the negative y direction, acting on the airfoil. For drag, we're looking at the force acting against the front face at the airfoil, so it's in the x direction actually. So to create monitors and plots, once we have our reports defined, we'll select both of them, right-click, and create a monitor and plot for each report. This will give us real-time visual feedback during our simulation. Our simulation is a steady state one, so we'll set a stopping criterion of 1000 steps. And we believe this should be sufficient enough for the simulation to reach steady state. We're going in with an assumption, kind of already, again, best practice. It's kind of, You think it's going to stop at 1000, we're kind of reaching steady state after 1000 or towards 1000. If it's earlier, we could have also like defined like 500 steps or 600 steps, but we'll see later on when we run the simulation when we reach the steady state. Once we have done that, we're going to go and run the simulation, clear, reset mesh, okay, and check if we have any issues with the mesh. And no, that seems to be all fine, so we are good to go. And before we run our simulation, we'll also set up some scalar scenes for pressure and velocity. And these scenes will allow us to visualize the pressure and velocity field during our simulation. Make sure that you have the residuals plot open, go to step, and then we are going to start running the simulation. And as the simulation runs, we can monitor the downforce and drag plots. Once the lines start to stabilize, we know we are kind of near, or we're kind of approaching or near our solution. You can adjust the fixed step stopping criteria based on your simulation's complexity, and always remember these settings can be tweaked to suit your specific needs. Now, as our simulation comes to a close, let's move on to interpret the results. Firstly, let's maybe compare very quickly what would have happened if we used other turbulence models, so K-1 or RST model. We can kind of, this article, for example, that I'm gonna show right now in this video that I have open, shows the validation of turbulence model in STAR-CCM+, which has basically been done they have done a comparison between different turbulence models available within STAR-CCM+ and compared the results with experimental data, which is always important. Guys and girls out there who are CFD practitioners, validation and verification is the keyword. As we move towards the results section, we'll find out that for the negative angle of attack, closest to the experiment is the RST model, but as we move into the positive angle attack region, as you remember, we used 5 degree. We can see that all models behave almost in a similar fashion. There's not so much of distortion in the values, as you can see. So right now this graph is for the normal force coefficient. Similarly, if we are further tilting away the flap, so they had actually a flap and a wing, so this is also behaving in a similar fashion. And the similarity is almost found in all of our results. There's not much difference that we will find, and we'll also validate this with our results as well. So if we move back to our simulation, so right now on the screen, we are seeing the results with RST. This is the pressure profile, and if we see it with K omega, it's almost the same controls in the same values, so not much of a difference. If we look at the velocity graph, it is behaving in a similar fashion too, not much difference, almost very identical results. There was some minor pressure difference like 0.67 and 0.684, but right now I would say that's negligible. Again, it really depends on what error is acceptable in your case. So this proves that our model is very accurate. The simulation that we have performed provides a very good baseline tutorial for further development, kind of investigating maybe 3D, maybe more complex wings and structures with this turbulence model. So let's close the RST one and let's discuss the results very quickly, the other results. So considering this pressure scalar field profile, the color gradient represents different pressure levels with each color corresponding to a certain pressure value. Now, what does this tell us about the airfoil? Notice the higher pressure at the leading edge on the front of our foil. This is because this is the first point of contact with the incoming airflow, so that physically makes sense. Would be weird if it's otherwise. As you might expect, the upper surface of the airfoil experiences lower pressure. Ladies and gentlemen, also be very careful to not argue with Bernoulli's principle, which is not that easy to apply for airfoil lift theory, but I'm happy, maybe let me know in the description if you want to have a separate video on how lift is actually generated and not only using Bernoulli's theory or maybe equal transit time theory to explain lift. Let's first look at the pressure scalar field. The color gradient represents different pressure levels with each color corresponding to a certain pressure value, as you can see. Now let's examine the velocity scalar field, and as the air approaches the leading edge, it slows down before speeding up over the curved upper surface of the airfoil. This is where the highest velocities are seen, represented by red colors in this plot. And on the bottom surface, the airfoil doesn't speed up that much, resulting in lower velocity compared to the top surface. Of course, if you want to compare to experimental data, what you could do, for example, is plot the points of the experiments, and there are some tools where you can kind of go to a paper and define the X and Y axis, pick all the points, and it saves you in a as a matte format or like in a CSV file, and then you can overlay the simulation result of maybe a line that you have defined across your profile and kind of have virtual probes inside of your simulation, virtual sensors, where you can kind of validate your simulations with experimental results if available, obviously. And maybe as a closing remark, note that the pressure and velocity distribution kind of depends on a few things. Obviously, airfoil shape, angle of attack, speed, and properties of the air itself. So once you tweak these parameters, you will actually see that the results also look different, obviously. So if you already did some CFD simulations, I think this should be pretty clear. But if you're a beginner watching this video, maybe play around a little bit with STAR-CCM Plus, or maybe a different tool of your choice, to kind of see how the angle of attack affects, for example, the flow separation. Cool, that's basically it, ladies and gentlemen. I hope that you enjoyed the first tutorial of this deep dive series. Let me know if you have any questions down in the description. I'll link every paper, every relevant information about the 6215 airfoil profile down in the description. Some machine learning resources, some resources how you can calculate Y+, what this ominous value actually means. And let me know if you'd be interested in more STAR-CCM tutorials in the future. And as always, keep exploring, keep learning, and as always, make sure to keep engineering your mind. Peace.